right, probability, third little subheading, theoretical probability. There are two probability types, experimental and the theoretical. All right, experimental, as it says in the title, it's actually probability based off the results of an actual experiment. Okay, and the theoretical probability is the based off of what you expect to happen in an experiment. So like expected probability, really. So most likely theoretical probability we will have to use when the sample is really big, and we just can't do the experiment on it. Okay, now let's have a look at what we are about to learn. The addition rule for mutually exclusive events. Now what is that mutually exclusive events? It means two events are mutually exclusive if they cannot both occur at the same time. That means there's no common events in between them, because they're not going to happen at the same time. There's no, meeting point there. So for example, the set of outcomes of a single coin toss, which can result in either heads or tails, but not both, because only one coin. Okay, so that's a mutually exclusive event there. And then we have formula there. Okay, well, I mean, it makes sense if I just push this one in here in the Venn diagram. I might just push it up there. Okay, so if there's no common ground, okay, they're all happening at the different, not at the same time, so they're all independent, like individual. So therefore, if we want A or B, we want to have it combined together. It's either just all of the A, all of the B, isn't it? So that's what it is. Now, if it's a non-mutually exclusive event, there will be some common ground there, which will be, we will have to say A and B are not mutually exclusive because there's a common parts in there. So when you add each part, and you have to take away the overlapping, repeating part. Okay, so then it's non-mutually exclusive event. But we are going to focus on mutually exclusive events. Okay, so example 1. Now this is a question is saying group A or event A is diamond cards. A deck of cards of 52. A is all the diamond cards, which is 13, because there's 4 suits. And there's 4 groups, obviously, so each one is 13 cards. When you do 13 times 4, it will be 52. So, and then event B is black cards. Now, the cards has a red or black. So, half of them is black, half of them is red. So, if I have to summarize this in a Venn diagram, let's see if I can do this. So I've got event A. Obviously this is a mutually exclusive event because they both cannot have any common parts at all. So here, diamond cards, how many? 13 out of 52. And this one, half of 52 is black cards. So we got these 2 events here. A is what? Diamond, okay, cards, and that's what? Black cards. Okay, so to find probability of A union B, I need to do probability of A, probability of B, because there's nothing to be comment about. Now, I just want to throw this in. Probability of A intersect B, like common part, obviously is 0, isn't it? So remember that. Okay, so when you do this, I'll just have to do is 13 over 52 plus 26 over 52, which will be 39 over 52, simplify 3 over 4. Oops, it'll help if you can see them. Okay, so that's what it is. And the second example is the given that probability of A is 0.7, probability of B is 0.3, and the A union B, the probability of A union B is 0.8. Determine whether A and B are mutually exclusive events. Okay, if they were, what can we say about them? So let's have a look. Probability of A union B, it should be probability plus, or I could say should be 0. Okay, so let's have a look at this part. So I'm just going to go with P A union B equals P A plus P B. Let's have a look what we got here. That's 0.8, 0.7 plus 0.3. Now that's 0.8, 1. Now that is not equal. Okay, so therefore A and B are not mutually exclusive events. Okay, so that's what I've got. All right, I mean, you could do some other ways, but I'm just going to stick with a simple way. Okay, next one. Now, there's a little parts I need to mention for this one. Is the complementary events. You probably remember this from year 9 probability. And complementary is a completely exactly opposite. And we write it with a little bar on the top. Now, with the complementary is like with not complementary, when you add it together, it'll be whole probability 1. Okay, so just to get the complementary event, they're just simple algebra. Sort of, I'll move this one to the other side. It'll be the one whole thing take away the opposite of the complementary event, if you know what I mean. Okay, well, let's have a look at the question now. If the probability that it will rain tomorrow is 0.2, okay, so 20%, what is the probability that it will not rain tomorrow? Okay, that is easy. All right, guys, it's easy one. So I will just go probability of not rain. I'll just put the little bar on the top, so it's complementary. So what's that going to be? It's going to be 1 take away probability of rain. So it'll be 1 minus 0.2. 0.8 is not rain tomorrow. That's the probability. Okay, so that wasn't really bad at all. That was easy. Okay, so last one for this little subheading. The probability that a traffic light will not turn green as a car approaches, it is 7 over 12. So not turning green is 7 over 12. So what does that mean? If I want to turn it to green, it'll be 1 minus 7 over 12, which is 5 over 12. I'll just put that in there because I read the question before you guys. A taxi goes through 180 intersections where there are traffic lights, all of them, okay, 180 of them. How many of these would be expected to turn green as a taxi approached? Okay, so we got that, luckily. So probability of turning green was 5 over 12. All right, so that's done. And 180 of them we're going through. And then how many of them? It's a 5 over 12, okay, which is 75. So therefore, I can say 75 traffic lights would turn green for this taxi. Excellent. Okay, well done, guys.